Welcome in, everyone. How's everyone doing today? Science. Yeah, today is our first episode of Science Sunday. You can see in the title, we're covering lasers. It was definitely interesting to research, but hopefully I can help you understand it. Right. Before we get into that, one, if you missed some of this, if you want to go back and see some of this, I will actually do some editing. It's strong, but I will cut it down into however long we cover this thing before we move on to what we're doing for the rest of stream, and that will be posted on YouTube today, tomorrow, something like that. Cool. Two, these topics are complicated, very complicated. If you have questions, don't be afraid to put them in chat. I will try to answer them as best as I can. Yeah, and if I don't understand something, or if I don't explain something, like I assume you know something and you don't, that's okay. With science, I don't know, we have a very poor basis for science in the US, so I will cover anything up until what you don't understand. Cool. Also, we have a blackboard, so hopefully some of the drawings will be easier to understand. Cool. Cool. Well, let's get. Oh, let me turn around. Let me turn on a music that's a little bit quieter. Jesus, it's loud. Cool. Might not be coming through. Okay, it is coming through. It's just quiet. Quieter than OBS wants to tell me. Cool. Great. Science. Fuck. I'm on the paint here. Oh, because it wants to erase. No, don't erase. Give me a thing. Yay. Okay. Here, let me pull up my notes. This has everything I need to cover. First, we're gonna cover some history. Laser. Laser is an acronym. It stands for light amplified by the stimulated how do you spell emission? 2 M's. Emission of of radiation. Okay, what does this mean? Okay, we'll get into that when we look into how it works and the things that go into laser. But basically, we make light. We amplify the light by, right? Emission, it's another word for make more. So we make something, amplify our light by stimulating, which is we nudge something towards making more light. So we have a thing, we make light, we tell this thing to make more of light. So we have light, and we want it to make more light. And, yeah, so we make more light by telling this thing, by stimulating it to make more. radiation is another. It's another way to say light, essentially. Okay. And okay, that's our first thing. Laser is an acronym. Light amplification by the stimulated emission of radiation. First, that's our first big thing. I guess importantly, we have to define what a laser is first. Laser? See, like, you would think that it's just, you have your box, you press your button, and it shoots out a beam of light. Very simple. Not a complicated concept at all. But the actual lasers can be defined in a couple of ways. You have your light, and this light is coherent. Coherent meaning that it is coherent means that it's all the same light. So right, you know how light has wavelengths, right? This is your wavelength, and if you have a big wavelength, you get a like a lower energy. Bigger the wavelength, the lower the energy is. So for example, red. Red is low energy. It's low energy light. If you have a shorter wavelength, you have a higher energy light. So for example, purple. Purple has one of the highest energies. Blue and purple are the highest energy visible wavelengths. But even after purple, you have like UV. I believe microwaves are up here too, above this. That's not how you spell microwave. Microwave. Sorry about this. Cool. UV, microwave, those are all high energy. Alright. Lower energy is like, you have infrared, IR. I think radio is even below this. Radio, then you have IR, then you have red through purple, then UV, and then microwave. Nope. Don't do that. Okay. So. We want a coherent beam of light, so all the same wavelength, so the same color of light, and we want it to be in phase. What that means is that, okay, so you have here one wave of light here, And then you have your second wave of light here, and your third wave of light here, and your fourth wave of light here. And because of how light works, when this happens, you get dips and peaks. So right here, for example, you'll see, right, these two, right, if this peak, okay, well, a better example is if you have your one wavelength here, and you have the exact opposite here, then this will cancel out. You will get no light. Because this and this cancel out to 0. This is already at 0. That and that cancel out to 0. That's already at 0 in this poor drawing, right? We don't want that. We want them to all be in phase, which means I have one wave of light, I have another one, and then another one, and then another one. They're all on top of each other. So all of these peaks will add. And all of these valleys will subtract. Okay. Because of how waves work, the lower the valley and the higher the peak, the brighter your light is. Even though the valley gets lower, it makes the light brighter. And for that, they all need to be in phase. So that's important. That is going to be our definition for a laser. Cool. Now how do we get all of that? Give me an eraser. Big. We have some history first. It's not the most fun, but it will help understand where this technology came from. So first, we have classic Smart Boy. What the hell? Oh. Uh-oh. That's not good. Yeah. Okay, you can't see it at least. That's good. Let me see. What the hell happened? Oh, I think I know exactly what happened. Is this loose? One of these things is loose, and it's not happy with it. Yeah, better. Okay, hopefully. Sign something. Sorry, the screen was being funky for a second. So we have Albert Einstein. He was smart. Really smart. So, even before really, like, any of this was thought about, he published a paper called the on the quantum theory of emission. And this paper essentially laid the groundwork for stimulated emission. Which, remember from our laser acronym, that's what lasers are. So he laid the groundwork for this concept, which would then be used in lasers. This was in 1917. Now, it wouldn't be a long time before we got lasers. But In 1953, Joseph Weber published a paper. I didn't get a name for the paper. I didn't find the actual paper, but I found people who described the paper, and it was about using stimulated emissions to make a microwave amplifier. Right? Microwave is one of the lights on our spectrum of lights. So he created a paper that was about using stimulated emissions to make light, specifically microwave light, amplified. Okay, well, I mean, microwave is light. So we have light, well, a kind of light, amplified by the stimulated emissions of more light. This is the entire part of our acronym. We're going to get into how this works in just a bit. Okay? So now we have kind of like the math on how this could work. In 1953, Charles H. Towns, James P. Gordon, and Herbert J. Zeiger, I think, made the first microwave amplifier. They made the device. And they called it the Maser. Okay. Maser is almost like laser, but instead of it just saying light, this stands for microwave. So it is a microwaves amplified by the stimulated emission of radiation. Cool. So they made a device that did essentially what lasers do today, but with microwaves. Then, in 1957, Jun Ichi Nishizawa. He proposed the idea for a semiconductor optical. See if I can spell this right. Optical maser. He said, what if we took that concept, but instead of doing it how they did it using crystals. What if we did it using semiconductors? Which are like the parts in like computers and stuff. It's like a switch, kind of. Basically, it doesn't conduct electricity very well, right? Semiconductor. It doesn't conduct charge very well. So if you have electricity through, it doesn't do this unless the voltage is above a certain amount. So that is why it's used in computers, because you can use a tiny, right, the electricity is both voltage and amperage, so you can use a little bit of amperage with enough volts to turn on the switch, or to turn on the conduction, to let a lot of current pass. That's why it's used in computers. That is not what we will be using it for. We're going to be using some of those simple properties, though. Those properties will be important. So, he said, what if we did what they did using crystals, but instead we did it using semiconductors? Because crystals are expensive and semiconductors are cheap and easy to make. Relatively. Then, at the same time, 1957, Towns, this guy, and Arthur L. Law began research on a maser for visible light. Visible light. Right? Microwaves, you can't see them. And so they were looking into applying that same technology that they used to make the maser for visible light. And at the same time, again, same time again, 1957, Gordon Gould. He was working on his doctoral thesis about the energy levels of excited thallium. Those concepts we'll get into later. But a lot of this, I know, a lot of this we'll get into later. But I want to get through this little bit of history first. And because he was working on this thing, in his notes, he had his ideas for how a laser could be made. Using two parts, both of which are essential to lasers. An open resonator and an optical pumping. Both of these, like I said, they're essential to how lasers work today. Lasers would not work without these. 1958. Bell Labs, which is where Shawlaw and Townes worked, they filed a patent for an optical maser. Which is what they were working on. In 1959, Gold published the acronym LASER in the paper, the laser light our entire acronym, light amplification by the stimulated emission of radiation. He first published this acronym. What he wanted was that other things that used this technology would be called would use like acronyms with the ASER for different parts of the spectrum. So you would have, for X-ray, you would have the Zaser. I'm not sure how one would pronounce that, but Zaser. For UV, you had the UVaser. And then for radar or radio, you had the Razer. People didn't do that though, because it's complicated. And so for anything above microwaves, we call it a laser. And then for microwaves, we still call it a maser. Okay. And this is a complicated part of just history in general. That the patents, which are kind of like who made what and who gets the rights to what, for all the parts of the laser are owned by a lot of different people. So it's hard to find a consensus on who really invented the laser. I mean, that's the complicated part with history. That's the risk with history. I mean, we'll wait for everyone to come back from ads. I didn't even see that. Red ad starts about here. Oop. Laser. Wait for ads to finish. Okay, welcome back from ads, everyone. Sorry about that. We'll start from back here for everyone who was in ads. He published a paper that included the acronym LASER, right? With the intention that for different parts of the spectrum, you had X-ray, UV, and then radio, you would have different ASER acronyms. So you would have ZASER, that's hard to tell, UVASER, and then RASER for the different ones. Nobody does that. If it's bigger than a microwave, it's called the laser. Otherwise, it's a maser. But it's an interesting bit of history. Now, the actual history of the laser, who invented the laser, all of that stuff, that's complicated because the laser, all of the different parts of the laser, their patents are owned by different people. So it's hard to find a consensus on who made the laser. A lot of people came up with ideas very close to the laser, but no one person, like historians, can't really give credit to one person to who invented the laser itself. Now we're going to get onto the interesting science stuff. How does the laser work? Well, there's a couple things we need to understand before we get there. First is the very common orbital model of electrons. Right? You have your atom, your nucleus, and then you put electrons in an orbit around it. Oh god, that's horrible. You have different orbits, kind of like the planetary system. Good enough. Yeah. Yo, Soren, thank you so much for the raid. How's it going? Welcome in, Raiders. Yeah, my name is Shadow. I cover science stuff. This is our first Science Sunday, where I'm going to be covering a science topic for like that I researched before. Today we're covering lasers. But normally I do coding, I play games sometimes. Yeah. forget that the lasers or that the lasers. I forget that the alerts are loud. I need to fix all of the alerts. Anyways, hi Soren, hi Raiders. Thank you so much for the raid. How was stream? If you didn't hear, I'm Shadow. I cover science, technology, this kind of stuff. Sometimes, mostly we do coding, and sometimes we play games. This is our first Science Sunday, where I plan a researcher topic beforehand, and then kind of teach all about it. Yeah. Right, today we're covering the laser. It's good. Did a bunch of grinding through 4 video games, so hopefully you'll be caught up for streaming the rest of the week. Well, I mean, I hope the grinding went well. I saw you were playing Warframe, right? I think that was when I was in, and then you were also playing Kingdom Hearts. Let me just circle. Okay, good enough. So, orbital model of the atom. Yeah, we did Warframe, Kingdom Hearts, Final Fantasy 14. 3 games? 3, 4, 7, it's all the same number. Right, so orbital model, you have your electrons here. Or your electrons are in orbit, right, around your nucleus on different orbital levels. And this is one model of the atom. It's a pretty good simplification of how this works. And we're going to be focusing on these outer electrons. These are called the valence electrons in the outer shell. So in this case it would be like this one, that one. We're focusing on those for now. The other ones, they are important for like chemistry stuff, but the inner electrons tend to do a lot less of the reacting, and they tend to be involved in a lot less. The valence electrons, on the other hand, are involved in a lot. This is the orbital model of electrons. We're focusing on this outer layer. Next, light and radiation energy. Also, sorry, I'm looking at notes because there's so much to cover that I don't want to miss anything. Light, right, we covered. You have your wavelength. So if you have your wavelength, this is your light. You have the wavelength. Pretend this is all even. This is your wavelength. Now, right, if you've covered like sine and stuff, the energy of a lot of things, for example, sound. Sound, the energy is really in the amplitude. The frequency does have energy in it. The higher the frequency, the more peaks you have, so the more your particle has to move. So more energy. With light, each photon, its energy is almost entirely based on the wavelength. So that is the only thing that matters to us. The other thing is that light, nah, that's not how you spell light. Light is equal to electromagnetic radiation. This means that light has an electric field and a magnetic field. And radiation means that it's going somewhere. So, right, you have your light source. Also, by the way, Raiders, if you need to rest, Soren, if you need to rest, take care of yourself, please do that. Yeah. You have your light source, and your light is leaving the source. That makes sense. That's all radiation means. Nope, not that. And this is going to be important. Light, electricity, and electrons, and magnetism are very closely intertwined. So no problem, you shall lurk for a tiny bit before we have to take off for food times. Well, have a good lurk. And thank you for the raid. Basically, you can take light, a light particle, which we call a photon. A photon is moving. It's going places. Because the photon is going places, it produces an electric field around it. So if we do all that, give me just something like this. You have your photon. Now, like, we're familiar with, like, a magnetic field, right? You have your fields. But there's also an electric field. Because, again, electricity, magnetism, and radiation are really... I won't say that they're the same thing, but they're very closely intertwined. And when you get really into it, they are essentially the same thing. It doesn't matter too much, besides that light is intertwined with electricity and magnetism. Last thing we have to cover is what's called energy levels, which we talked about in the history. Energy levels is you have your particle, or here, you have your nucleus is like somewhere down here, right? It doesn't really matter, but something like nucleus is all the way like down here. There's the fill. The nucleus is down here. Then we have our valence level. We're not going to draw the other ones because we don't really care about them. Not for this, at least. You have your valence electrons, and they live here. Right? You have valence electrons. Now, if these electrons were to get really excited, they can move farther away from the atom. Because right now they're locked in this orbit. They're stuck here. They don't have enough energy to get farther away. But if they did somehow get enough energy, they could jump up to this one. Or this one. It's kind of like how a satellite, if you make the satellite go faster, it can orbit farther away from the Earth. So some satellites can stay in high Earth orbit, some in low Earth orbit, really close to the atmosphere. It depends on how fast they're going. It's pretty similar for electrons in the fact that the more energy they have, the farther away they can be from the nucleus. The only a really big difference is that electrons can't be here. This space, they're not allowed to be there. They have to be here, here, or here. They can't be in between. So, if an electron were to get energy, it has to get just enough energy to jump up. Exactly one, or jump up all the way. For example, if it were to, right, electrons can get energy from light. So if my electron were to get hit with a beam of light that had enough energy to jump it up here, but the next kind of rung in the ladder is up there, the light would just pass through, and the electron wouldn't interact with it at all. But if it were to get hit with another beam of light, let's say this one has, say this distance is 3 joules. It's not. It's a very small amount of energy overall. Right, we're talking on a very small time scale, but we'll call it, this is 3 units of energy. 3 units. This photon has 2 units. So the electron ignores it. This photon has 3 units. When the electron gets hit with a photon that has enough energy to jump it up one or multiple levels, it will absorb the photon and jump up the level. It will go up here. So the electron can only jump if and only if the light beam that hits it has exactly enough energy to jump it up. Another way that electrons can jump up is with a electric current. So, right, the electron wants to jump up to this one. If you put enough voltage you can think of it like force. If you put enough voltage to jump the electron up, the electron will jump up. And when it does that, we call it excitement. The electron is in an excited state, whereas here, this is ground state. This is excitement level 1, this is excitement level 2. Cool. Now that is really important to how lasers work. Now, if an electron, right, so here's our ground state, we'll call this G, and this is our excited state, E. If our electron is here, and right, like if you have a satellite in orbit and you stop pushing it, eventually it'll fall, right? It'll fall out of orbit, but it'll slowly get closer to the Earth because it does lose some energy eventually. Electrons work kind of similar, again, but not quite. After a certain amount of time, when the electron loses enough energy that it can't stay up here in this orbit anymore, in this excited state, it will jump all the way back down to ground. And it will release light that has the same amount of energy that it needed to jump up. So if we have an electron, this electron is in ground. We hit it with, say, that's too close to the other one. Let's see here. Ground, and we hit it with, say, light of 3 units. This is our excited state, and that is 3 units away. The electron will absorb this, jump up, and become excited. Then, when the electron eventually loses just enough energy that it can't stay up here anymore, it will jump down and release light that has 3 units. Now, because both photons have the same energy, they have the same wavelength. They're the same color. Because remember, that's the only thing that can affect the energy of light is the wavelength. So if this photon has 3 units of energy and is, I don't know, green, then the photon that's leaving when the electron jumps down will have 3 units of energy and be the same green. Now that's pretty cool. That's called... I have the word, but I forgot it. Spontaneous emission. Because the electron jumps down spontaneously and emits a photon. But that's not what we're talking about. We want stimulated emission. Stimulated emission works a little bit differently, but it's the same concept. You have your ground state, you have your electron in the ground state, and then you have your excited state. This is excited. And these are, again, 3 units away. So, if the electron gets hit by a beam of light that has 3 units of energy, it will jump up and be here. So, same process as before. Gets hit with light, it absorbs it, it jumps to the next state. Now, if this electron that's excited gets hit with another photon with the same energy, something interesting happens. The electron will jump down and release not 1, but 2 photons of the same 3 units. Now that's cool and all, but I mean, we gave it 2 photons, and it released 2 photons of the same energy. So we gave it 2 photons, it gave us back 2 photons. That's great. Why does that matter? Because these 2 photons are now in phase, even if these 2 photons were not. These 2 photons, let's say the phase is, I don't know, 3. It doesn't matter what phase this light was. Let's see, can I? It doesn't matter what phase this light was. This light was phase 3. So both of these photons are now in phase 3. And that's important because for our laser, we defined it as, well, all of the light has to be in the same phase. So now we know how to do that. The question is, well, I mean, if we have this, it produces two... not that. You have your electron system, right? You have your electron. This gives us 2 photons. Well, what do these photons do? They hit another electron that's in the ground state, and the electron absorbs it. That was a bad box. It hits another electron that's in the ground state, and it absorbs it and goes into the excited state. Which is not what we want. We want the light to stay around so that it can leave. Because we do want to get... Somehow, we need to get the light to come out here. And we need like a lot of it to come out this end. If all the light were to just continue being absorbed, that wouldn't happen. So, what we need is... And this is the thing with all, like, when you start getting this small, nothing is about something will happen. It's about making sure something is more probable to happen than not. So what we want is for it to be more probable that an electron is in the excited state. So when it gets hit by the photon, it gives us 2 photons that are in sync. Then for it to be in the ground state. So that if it were to get hit by the photon, it would eventually only give us 1 more photon. We want this to have a higher probability. Oh my god, that's so bad. Higher probability. Okay, now this is what a graph, let's say we have a graph. This is ground state, this is excited state 1, this is excited state 2, and this is excited state 3. What does this normally look like? This is the majority of the electrons. Some of the electrons are up here. Some of the electrons are up here, and some of the not like this. It's more like some of the electrons are up here, and even smaller some of those electrons are up here, and an even tinier amount of electrons are up here. This won't do, because if we have excited electrons that come from here, they hit ground, they will... actually, we don't care about these ones for now. We will later. Not all elements have a second and third excited state. So for right now, we only care about this. What if we just erase this? Good enough. What the hell? Oh. We have our excited state 1 and our ground states. Soren, okie dokie. You shall have to rest for a bit. Take it easy and have a great of your stream, man. Thank you. Thank you for the raid again, and I hope you have a great rest of your day. Okay. So right, we have excited state 1. So we have electrons here, and they will make light. So this will make some light by stimulated emissions. That light will hit ground state electrons and make them just jump up to the excited state. But that won't do, because most of our produced light is getting absorbed. What we need is for it to be the other way. We need this much here, and, oh my god. This much here. Oh my god, stop. We need this to be like this. Oh. This one. We need this to be like that. This is what we need. How do we do this? Well, this is what we will call pumping. We need to pump electrons from here up to here to create what's called a population inversion. Because we took the population of electrons and inverted it. Now more are on a higher excitement than on the ground state. This is population inversion. Cool. And what this does is that most of the photons that get produced by this will either go on to hit other excited electrons and make more photons, or they will leave. So now if we have our thing, we have our, I'm gonna start writing electrons like these now. Is that like sometimes you have your electron that produces some photons. Now some of them are still ground state electrons. Again, probability. We don't need to completely rid the ground state of all electrons. We can't do that. But we need to make it mostly excited electrons. So in this one, produces a beam of light, or produces two beams of light. This light will hit another excited electron, produce two more beams of light. This one will leave. This one will get absorbed. And that's okay. That'll happen sometimes. But then this one will go on to produce two more beams of light, and this one will get absorbed. So now we have two beams of light. They reach the finish line. And then we have a laser. We have our nice laser here. That, because most of the light, even though some of it will hit ground state electrons, most of the light will leave. Okay, in this case it doesn't look like most of the light, but like with a good enough population inversion, then you can get a strong laser. Also, this process of taking an excited electron, making it to ground by hitting light, this was stimulated emission. This is also called lasing sometimes, or it's like the process by which this happens. So the part of the machine that creates this, yes, I know, the part of the machine that creates this is responsible for the lasing. Because of course we need more words. That just makes everything easier. Okay, so we have our population inversion. We need that, and we need that because it'll make it more likely that our photons actually get to escape. How do we make a population inversion, though? Well, we have our material. Say this is a crystal. Let's say this is ruby, because that was the first laser. You take your crystal, and you just need to take a shit ton of energy and shove it into the ruby. Rubies are not conductive. They do not conduct electricity, so you can't apply a voltage to the ruby to get the electrons excited. What you can do is shine a really bright light. Let me see if I can find it. I believe I have an image of the first laser. First ruby laser. Original. Huh. Okay. Basically, what they did was they took their ruby and they put a light source next to it. They used what's, I believe, a xenon flash lamp, which is just a lamp, you know, like fluorescent lights? Or like neon, not fluorescent, neon lights use a gas, right? They use neon gas. And then they have, and then they put like, you have your battery, you connect it, and you put a voltage through the gas, and the gas glows. They use something like that with a gas called neon, or xenon, not neon, xenon, which produce a lot of white light. And that white light is made mostly of light we don't care for. It doesn't matter to us. But some of that light is light that actually matters. So, we take our electrons that are in ground state, and most of the light they're going to ignore. Most of the light they don't care about. But some of the light is just right to make it jump up to an excited electron. And once that happens to enough of the electrons, this is called pumping, because you are pumping the electrons from the ground state into the electricals, or into the, not electrical, into the excited state. You take your light, and most of that will, right, it was just open on the back, so most of that light would get to leave the back here. Most of this light would just go through, but some of that light would do this, and then you would just start it with one beam of light that was also right, and then you would start getting your chain reaction. So you would get your 2, and then this would produce 2 more, and then you have your light. And now this is great, but you wouldn't get very much light if you only had it bounce around, like, or if you only had it just go through. That is because ruby is made mostly of a clear material. Right, most of ruby is made of nothing, but some of it, like in a very pretty even distribution, is made of chromium. Chromium electrons are the ones that do the process of lasing. The rest of the ruby is just there because, one, chromium doesn't let light pass through it on its own, and it gives it a crystal structure that lets all kinds of light go into and touch the chromium. Cool. We take these electrons that are producing these lights, and right, if they were to just go through, then you would only get whatever, like a couple beams of light. Photons, you cannot see individual photons with like, not without like super science tech and stuff. So what you do is you take these photons and you put a mirror on both sides. Both sides. Let me draw a box better. This is your ruby. This is what's called your gain medium. A medium is just like a thing that other stuff can pass through. In this case, light. It's called your gain medium because it does this amplification thing. It'll turn your one beam of light into like 5 beams of light, which is cool. But the problem is 5 beams of light is not very much. You can't do that much with 5 beams of light. So what you do is you put a mirror on this end. And you put a mirror on this end. This mirror is completely reflective. This mirror is 99% reflective. So a tiny bit of the light, 1% of the light that comes out of this mirror, or 1% of the light that hits this mirror will go through it. Which is how you can get your beam at the end. And then you have like a lens here to focus all the light. But 1% of the light will go through. That's important because you still need it to bounce around a lot. So now, the light will go, you have light, then it'll become like 5 beams of light, then this will get multiplied by 5, and it'll go back and get multiplied by 5 again, and then go forward and get multiplied by 5 again. And this will keep happening a lot. So you get your laser. Now there is one small issue with this setup, or one other factor to this setup. Not really a small issue. Besides the fact that you need like a flash lamp here, so it's not super like portable or anything. It can only be really used for some stuff, and it wasn't a very high power laser at the time. The other thing is that when this mirror would bounce light back and forth, if the light wasn't exactly the right wavelength, so for example, if my light was exactly the right wavelength, it would get bounced back and forth and create what's called a standing wave. What that means is that the light that's in here doesn't go anywhere. It stays in place. All the photons, because they're all in phase, will follow this path. And so they will all stay inside of the device. The device didn't have shielding around the outside of the ruby. But, and like that's important because, one, the xenon flash lamp could shine the light through the ruby. And two, if your wave isn't exactly in sync, that's a bad wave. If your wave isn't exactly in sync, then where does this go? This goes up here, and then this just leaves. So other light cannot stay inside the laser. So, the two things that define what light a laser produces are, one, the energy between these two, which is usually measured in electron volts. The other is the distance between these mirrors. They need to be exactly the size of the wavelength that you want to produce. Or not exactly the same size, because wavelengths are usually pretty small, but exactly the same, like they need to fit neatly into that. Your wavelength, if your wavelength is 2 millimeters, and your mirrors are 11 millimeters apart, this wavelength does not fit in here. Essentially, this wavelength needs to divide this number evenly. So, for example, a 10 millimeter would work just fine, because 10 can be divided by 2 evenly. So first, this matters. The thing is that because of how electrons work, because it's all quantum physics and stuff, it's not exactly one energy. It is very close to exactly one energy, but not quite. It's a little fuzzy. So there's a little bit of wavelength, a little bit of wiggle room for the wavelengths you want to produce, or the wavelength that the actual gain medium produces. And you can cut those down by the size of these mirrors. Because if you want one thing, I don't know, this is like exaggerated, but let's say you produce both 1, 2, 3, 4, or let's say you produce, like 2, 3, and 4 millimeter wavelengths. I only want 3. So I need to find a length of mirror that is divisible by 3 and not 2 and 4. So I could say 27 millimeters. 2 will hit the 2 will bounce around inside of here and eventually escape. 4 will bounce around inside of here and eventually leave. 3 is the only one that's allowed to stay inside of my mirror. Because 3 millimeters is the only one that can create a standing wave inside of the mirrors, it's the only laser beam that we're going to see. It's another method that you can use to kind of cut down the wavelengths that your laser produces. Okay. Now, there are, obviously, complications. Because nothing is ever simple. Everything is complicated. So, we have, right, what I showed you was you had your ground and excited states. These were the only two. Our ground, oh my god, our ground is out here, and our excited is here. And this is great, because we can pump this, and cut the ground in half, and, it works. But that takes a lot of energy. I don't want to use that much energy. Also, electrons that are excited, when I do this pumping, when I pump, the electrons from ground to excited, they only stay excited for a very short period of time. That is bad. Because it's all about probabilities. The longer the electron can stay in this excited state, then the more likely it is to be hit by another photon and then do this stimulated emission. So, we say, okay, well, what if we introduce a third level? So this is E1, now you have E2. E2 is here. We could do the lasing between this and this. This could be our laser, if we wanted to. But then we run into the same problem that things up in E2 really don't want to stay up in E2. They want to fall back down to E1 really quickly. So, what we do is we say, I'm going to pump electrons from ground to E2. This is our pump. electrons go from ground to E2. And then, very quickly, they fall back down into E1, where they stay for up to 1,000 times longer than if I were to just pump it up to E1. So if I were to pump it up to E1 directly, it would stay for, I don't know. Okay, again, just to make it make sense on the human timescale. Let's say it stays for 2 seconds on E1. It doesn't. It stays for like microseconds, nanoseconds. Let's say it stays for 2 seconds. Now it's staying for 2,000 seconds. 2,000 seconds is a lot of time. There's a lot of time for a photon to come and hit this and do the stimulated emission thing. So this is pretty cool. But again, we need to create a population inversion between E1 and ground. Remember, all of the electrons are on ground. To start with, all of them are on ground. Lasing. For the 2 layers that we want to do lasing with, there needs to be population inversion. And because all of the electrons start on ground, we need to pump a lot of electrons. This is bad. This is hard. This takes a lot of energy and can be relatively inefficient. So, what if we add another level? And wait, there's more. We add another level and say something like that. Okay, good enough. Ground E2 E3. Okay. Now, we're going to pump up. Okay, we're going to reset our diagram. We have G, E1, E2, E3. All of the electrons are here. Some of the electrons are here. Very few electrons are there. And a tiny amount of electrons are there. Some of the electrons. Oh. Okay. Alright, you get it. And then we can say, well, now we have another level to play with. So instead of saying, well, what if we, instead of lasing between E1 and ground, instead of lasing like this, what if, because this takes a lot of energy, I have to pull a lot of electrons from ground. What if I just lase between E2 and E1? I mean, look at how many electrons are between E1 and E2. Not that many. So I can pull electrons from ground that go into E3, then they fall into E2 and make it bigger than E1. And now look, there's a population inversion, but ground still gets to be big because we don't want to take all of the electrons from ground because that's hard. Easy is good. So, because we have a population inversion between E2 and E1, we can do lasing. Oh my god. Same process as before. Lasing. Same process as before, but instead of going from E1 to ground, right? Instead of this being ground and this being E1, this is E1 and this is E2. Basically, we're minimizing work. Less work we have to do, the less energy it takes, the more efficient the laser is. Sure, there's less electrons we're playing with total, but we don't need a laser that uses all of the electrons. We only need to use like some of them. For example, like the laser point, well, okay. But lasers don't need to use all the electrons. They don't need to be that powerful. And this is so much more efficient that is 100% worth it. So, this is our most efficient. It's called a solid state laser. That is one type of laser. We have 3 more types of lasers to cover. They all use the same principles, but are slightly different. However, there are ads in 1:30, and I need to go to the bathroom. So those are going to happen at the same time. Cool? We'll put you on. Be right back. We're going to turn the music up. Okay, hopefully a little bit louder than that. Something like that. Cool. And then we'll get back to this once ads are done. Alright, see y'all in a bit. FBI, open up! Jesus Christ, Dino. Thank you so much for the raid. But, sorry, we're in the middle of ads. I think most people might be in ads. I'll say sorry about that. It shouts you out like 4 times and I don't know why. Yeah, hi Dino. Hi, Loris. Hi, Jamin. Welcome in. How'd the stream go? Welcome, Raiders. For those of you who don't know, I'm Shadow. I do coding stuff. I play games sometimes. And right now, we're doing a new thing called Science Sunday. That's what I'm calling it. I research a topic, and then on Sunday, I explain it. Today we're doing lasers. Also, thank you for the follow, Pesci and Red. I really appreciate it. Dino stream was good, chaotic. I need to read these messages. Zaman. Insert Delper's raid message. Hi, Zaman. Hi, Teddy. Hi, Red. Yeah, ad break should be over soon. Hopefully everyone's back from ads. Let me turn down the music. Okay. Yeah. We're explaining lasers. We covered like the basics of lasers. And we're about to cover some of the other types of lasers. And hi, Suo. Chat was in jail for about like 3 minutes. Thank you for the follow, Eve. Dino, everyone better be taking notes. Maybe. Hopefully I explain it well enough that we don't need to look at it again. But if you do, I mentioned this at the beginning of stream, I will be like chopping the stream up into like when we were doing this, and then if we have time, we'll probably be playing some like Warframe. So I'll cut this, or I'll cut the VOD into sections like this. So hopefully it'll be easier to look at it. Oh my god, what is that? 5 gifted subs? Thank you so much, Dino. So many. Jesus. No, thank you, Dino. I really, really appreciate it. Who got a sub? Ghost, Tiny, Kettle, Salmon, and Loris. Yeah, Dino, I really appreciate it. I don't even know what to say. Is your apology for having the raid and run? No, don't apologize. I appreciate the raid. If you have to raid and run, please do. Take care of yourself. It's important. But yeah, if you want to stick around, you can stick around. Then hopefully you learned something. Hi, Cattle. Welcome in. Thanks for the sub, Dino. Yeah. Dino, you gotta go eat dinner. Believe you tabbed. Thank you. I appreciate it. I completely lost my train of thought. What was I gonna say? Yes. Okay. Yeah. See, I have notes. Because we're covering stuff. Salmon, Shadow, can I call you Sensei as a bit during the stream? You know, if you want to, sure. I'll take that. An infrared pyrometer works to tell temperature. I'm like 90% sure it has something to do with how the reflection of an infrared laser works, but I did not look into that when I was researching for this. Maybe once we finish this, we can look into that. I think it's all related. Probably. What was it? Yes. Okay, so, for Raiders and everyone new, we covered solid-state lasers, which are lasers that have a crystal substrate. This can be like glass, other clear things. And that's just there to hold to hold everything else in place. That's not super important. What is important is the material that's inside. Generally, these are called like impurities, even though it's what makes rubies red. This is chromium. Chromium ions are in the special state where they can do the lasing pretty well. Right? You shove light in here, you take electrons from ground state. I believe it's a two-system laser, but I may be wrong. It takes electrons from the ground state, pumps them up to the E1, so that we can create a population inversion, and so that it's more likely that a photon that's traveling through the material will hit an excited electron and make more photons that are all in phase and of the same color, rather than hit a ground state electron, which will just absorb the light. And then, it'll become an excited electron, but not quite what we want. Examine different temperature things emit different wavelength infrared light, and that's how it works, by catching the light or something. Maybe? I don't know. I thought it had something to do with lasers, but that might be something different. That might have been like communication stuff. Anyways, so we covered solid state lasers and pumping. And next is gas lasers. Gas lasers are almost the same concept, but slightly different. You have whatever helium, I believe it's a helium neon gas laser, I think is the one that's super common. All kinds of stuff. HENE gas laser, right? Yes, helium neon. That's one of the more common like gas lasers. Basically, now there are two atoms here that have two energy, or two like electron states things. So you have this one. Oh my god. This is your ground state in helium, and this is your excited state for helium. And then for neon, this is your E1, or this is your like E2, this is E1, and this is ground. So what an electron will do is you take electricity, electricity or light. I believe these are, well, I actually don't know. you pump the electrons up somehow. I didn't look into these ones too much because they aren't used that much. They are used for some things, but not that much. You pump the gas up, or you pump the helium's electrons from ground state into the excited states. Then as collisions happen, because energy transfer and stuff, the helium pumps the excited states here is the same as the excited state on the neon. So the helium will take its electrons and they will put electrons in the E2 state for neon, and then it'll fall down. You get your E1 state. Then you have a population inversion, which lets this kind of work. And then you have this. This can fall down from E2 to E1, which releases your light if it gets hit by another light. So it releases two lights, and this works. It's very similar to how it would work in a solid state, but because the energy is being transferred from the helium to the neon, you don't have to go between E1 and ground. You can go between E2 and E1 and still get kind of like a benefit of it staying in E2 for a longer period of time. Okay, we're going to go over one other type of laser that is less complicated, and then we're going to go into the really, really complicated one. And I'm going to try to explain as best as I can. But first, we have, it's called free electron lasers. These use, right, normally we're working with electrons that are attached to atoms, right, and so we can move them around kind of, but they still have to stay attached to the atom. Free electron lasers don't do that. They have electrons that are going around in a particle accelerator. Particle accelerators are like CERN. That's the only big one that I know. But particle accelerators, they use magnets to take subatomic particles and move them almost the speed of light, like on a relativistic times, speed, it gets really close to the speed of light. So you have your particle accelerator. Let me draw this better. See if I can draw this better. You have your particle accelerator that does like, and you have, hi Rosie, welcome in, thank you for your daily cast. You have your electrons going around in a circle. Sorry I'm not responding to comments, I will get to that in just a second. You have your electrons that are going around in a circle, circle. Now that's cool. These electrons are going stupid fast. As lesson in particle accelerators? No. Lasers. We're learning about lasers. Okay, wait, back. Teddy, that could be spectroscopy you're thinking of. I'm running how a temperature gun works. The same thing. Temperature is about atoms moving too much and having too much energy. The atoms release that energy. Extra energy through light. The more energy they have, the smaller the wavelength of the light emitted is. Yeah. But I do believe it's a little bit different for the gun because it doesn't have, like... It can view the, temperature of things that are farther away than it should be able to... than the IR light should be able to go. Theoretically. I don't know this, though. That's what I understand about how those, like, I believe cameras use just view the IR light. How's that information released from going back to the original state get given back to the temp gun without all the energy getting refracted everywhere? Yeah, I don't know. We can look into that. Right. Free electron lasers. You could also call these wiggle lasers, because they make laser by taking your electron. Your electron is moving very fast. You have a stream of electrons that are all moving very, very fast. And right, remember when I said electricity, magnetism, light, all very closely connected. So you can move electrons by using strong magnets. So what you do is here. Get rid of that. You take your magnets here, and you have them alternating. We'll use like 4. Good enough. Right? You have your north, south, north, south, north, south. So now when an electron goes through here, it wiggles. That was horrible. It goes up and down. It gets accelerated in a direction because of the magnets. The thing with electrons and any charged particle is that when their energy state, essentially, like, an electron has a certain amount of energy. When that changes, or its form changes, it releases it somehow. And generally, it can either release as heat or light. Generally, for particles this small, it'll release it as light, because heat only really works for big like bigger things. Electrons don't quite follow the same rules as like atoms do, because they're tiny, and quantum physics is a bitch. But so you have your stream of electrons. Stream of electrons. It gets wiggled, and because it gets accelerated towards the North Pole, and then gets accelerated and accelerated and accelerated, each one of these releases light. Now there are thousands of electrons. There is a lot of electrons in this tube. Thousands, millions, billions, a shit ton. Thank you for the follow, Yami. I really appreciate it. How are you? I assume you came from Dino Raid? Because you have so many electrons, and they're all moving at slightly different speeds, right? One electron might be moving at 97% the speed of light. This could be moving, I don't know, maybe like, and this one's moving at 97.2% the speed of light. But because you're going so goddamn fast, it doesn't matter. Like how little the difference looks, it's a lot. So you produce a bunch of wavelengths. You produce light in a distribution curve, a bell curve. That's good enough. This is the most frequent light, most frequent frequency that you'll get. The most common frequency you'll get. And this, you can adjust this based on how fast the average electron is going. So if on average all of the electrons are going, I don't know, like a speed, let's say 93% the speed, 93% the speed of light, then it'll produce one kind. Then your majority of electrons will produce one kind of wavelength. So you get a nice bell curve. Now this is great, but this isn't a laser because it's not coherent. It's all not the same laser, and they're definitely not in phase. So we resort to actually some pretty relatively simple physics for once. This is the only type of laser that has less complicated physics. I think this is the least complicated one to understand. Basically, how do we know that they travel at 93% of C? Science equipment and stuff. They have measuring tools and like those big and the particle accelerators. So they say they can speed it up to a certain speed before they let it go into the it's called the undulator or the wiggler because it wiggles the electrons. So when the electrons move and they make photons and the photon is traveling, it passes the electrons relatively quickly. Again, the photon is traveling at the speed of light. The electrons are traveling at 90-something% the speed of light. Relatively fast, though, because, again, 1% the speed of light is some 300 meters per second. So the photon, why don't we write, photon is like, our photons are like tiny dots. Okay, our photons pass the electrons, and because photons are electromagnetic radiation, they leave behind an electric field. Or they create an electric field, which it's hard to draw like this, but essentially it takes electrons that are moving too slow and producing lower or bigger wavelengths than these photons. It takes these slow electrons and gives them a push to speed up, and it takes fast electrons and gives them a push to slow down. And now all of the photons do this. Even the ones that are all the way right on your bell curve, even the ones that are here and here, even the ones that are like here, here, and like here, they all do this. But the one that does it the most is the one at the top, because there's the most of that photon, or that wavelength of light. So what it does is it takes your bell curve and it makes it smaller. And then it happens again, and obviously because we're pushing slow electrons closer towards the middle and fast electrons closer towards the middle speed, we make the bell curve smaller again, until eventually there is one wavelength, and that is it. Essentially, one wavelength. And that's how you can get exactly one wavelength from this, I should not have erased this, free electron laser. But now, they're still all out of phase. And this is the really, I think, the most interesting part about this. Is that the phases also do the same process. Oh yeah, that distribution is not normal. It is the opposite of normal, because the normal pushed it to do that. But yeah, so you get a very like the it selects for the highest frequencies essentially, and it pushes other electrons to move closer to that right speed to get that frequency. Now for phase there is no distribution. It is entirely random. Right? This is your let's say this is your distribution of phases. It's random. There's no way to kind of pre-select for that beforehand. But this gets into math theory, kind of a theory. It's that if I'm taking a walk, right, and I select which way I want to go completely randomly, could go left, could go right, could go left, I could go right, I could go right again, then I could go left again. But now if I go left, yes, left, and then I go right again. And then I go left and left again, then I go right again, then I go right again. I am eventually going to reach the left wall. Because it is random, but the initial anomalies that happen lead to have a much larger effect on the overall distribution than at the end, than anomalies later. Let's see if I can pull this up. I should be able to. I have it in here somewhere. Side projects. Yes, this one. Oh yes, chain models, Markov walk. Okay, I do not. I did get rid of it. Anyways. You can simulate this. If you do it completely randomly, these initial anomalies early in the life cycle of this walk affect the walk way more than anomalies later. So eventually, one of the phases will be slightly more prevalent than the other phases because of random chance, and that phase will then push the other phases or other electrons to be close to that phase. Basically, like the electromagnetic or the electric field will. You could think of it that it kind of looks like this. So, some electrons are here already, and that's great. But electrons that are up here will get pushed to be down there. Electrons that are here will get pushed to be closer to there. So even if your initial electron spread looks something like this, completely random, eventually, after we do this process, your electrons get bunched into these groups. Here, let me see if I can match it up. You have your group, and then another group, and then another group, and then another group. And all of these groups, because it's bunched into nice groups, now all of the photons produced, one, they are already all of the same frequency, and now they're all of the same phase. Laser. It's essentially you just set the average speed of your electrons, and the laser just kind of happens, which I think is really cool. Besides also needing a wiggler. The wiggler is very important. You need your electrons to wiggle. Oh my god. But you set the speed, you set the wiggler. Oh, phase? I can probably explain this. Phase. Um, it has to do with the math equations for the actual, like, wave itself. But you have... Right, this is a quote-unquote sine wave, okay? My math sucks, or my drawing sucks. This wave has we call it a phase shift of 0, because this is your... Yes, essentially. But what that does is, for our purposes, it moves the wave. Oh my god. Okay. I'm sorry. I'm trying to draw. I just suck at it. It moves the wave this way. So if I set the phase shift to... Actually, there's a reason I have Desmos. Phase shift to, like, 2, it moves. Let's see if I can do this on Desmos, though. Desmos. Okay. Home. 1. It'll be easier if we do things in negative, I don't know, 4 pi to 4 pi. 4 pi. Well, that makes things easier. 2 steps of pi. There we go. Now, well, it's because you can kind of envision it like... What the fuck? Okay. You can kind of envision it like the actual particle is moving up and down. It's not actually moving up and down. It's moving between energy levels. It has a certain amount... It's not really a good way to describe it without getting into quantum physics. Because it is entirely quantum physics. Okay, we'll do a little bit. In quantum physics, a particle, any property of a particle... how do you even do the thing? I think it's like that. It's defined by this symbol, called the wave function. And it states where a particle will be at a certain point in time. It also states other things depending on the particle and the wave function that you're using for it. But the wave function is for a particle. For example, right? You may have heard of this thing called the double slits experiment. Is that if you have a wall here, and then, right, so this is your box. Again, sorry about the drawing. Okay, there. This is your box. We'll just ignore all of that. You have a wall. You have another thing here, and this has 2 very small holes in it. The light would go through, and you would expect to get kind of like a rectangular thing like here. Kind of just like a light that slowly shades out. You don't. You get something that looks more like this and this. No matter how close the slits are to each other, the light dips in between them. That's one part of it. The other part is that, like, if you make a really small slit, you would expect that the light, if you have a hole in here, and I throw a basketball through the hole, it'll go through the hole, and if it hits the other side, it will leave. The basketball, from this position, cannot end up here. I would have to throw it from here for it to end up there. Yes? Hopefully that makes sense. Light doesn't behave like that. I can shoot light through this hole like this, and the light can end up here, or here, or here. And it's really hard to predict where it will go, because it will go somewhere. Where is the question? And that is what the wave function predicts. It says, okay, so if you were going to shoot the light through here, the photon on your backboard has a low chance of being all the way over to the right. As you get closer to the center, it goes up and then back down. It creates a probability distribution curve for where the light is supposed to end up. And it has a chance to be anywhere in those positions, and we can't know for sure until we observe it. Yes, exactly. And because of that, see if I can find a better explanation, because I don't think I'm going to get better than that. Does the photon really move in a sine wave? The wave length about then what t does it describe? Okay. Okay, so remember how we said that light is electromagnetic radiation? Okay, so ignore this part. The sine wave is the peaks of the electric and the magnetic field. Light does both, and the sine waves and valleys are the peaks and valleys of those fields. So for example, right, it'll be easier to visualize with an electric field. So an electric field could say, hey, we want the electron to be there. Okay, we're pretty neutral. We really don't want the electron to be there. And then we're pretty neutral. Essentially. Because of how electrons work, they aren't in a place, same as the light. There is a probability distribution for it to be anywhere, but it is most probable to be in certain areas. And what the bands are where it's not so much levels. Actually, we aren't going to get into that. But all you have to know is that light, this is the peak of the electric field, this is the valley of the electric field, and these are neutral positions. The electric field really wants an electron to be here, doesn't really care. Or no, the electron doesn't really care, really wants it to be there. Doesn't care, really doesn't want it to be there, and then also doesn't care. That's what the sine wave actually represents, which is why the frequency has to do with the amount of energy that the light has. That is more complex stuff with like quantum physics and everything, and I don't even know that much about it. I know some things, but not that much. Okay, right. We did the solid state lasers and the gas lasers. And then we did the free electron lasers. Now, this is at the same time the most common laser and the most complicated laser. At least that I could find. There's probably some other wacky designs out there, but these are the ones that I found. Conductor lasers. These lasers, yeah, because the thing is, it's the most complicated to explain the physics behind, and it is the most, but it's also like probably like the easiest to build overall. Because, right, ruby is fucking expensive. This is just silicon. Silicon is cheap as shit compared to rubies and other stuff. So you can put semiconductor lasers in everything. So like your like a laser pointer for your cat and stuff, that would all be semiconductor lasers, which is why it doesn't cost you hundreds of dollars. But at the same time, while being the most common and being the easiest to make, the physics can get kind of complicated sometimes. So first, we're going to figure out what a semiconductor is. I mean, you can just kind of break it down. It's kinda conductive. But it's not kind of conductive like it's okay at conducting. It's really good sometimes. And bad other times. So, for example, silicon is what we would call a semiconductive material. It conducts electricity sometimes. Basically, remember those bands we talked about? How you can be in ground state, oh my god, ground state, or an excited state. Silicon, like everything else, does this too. First we're going to explain metal, and then we're going to explain why silicon is different. Metals are conductive all the time. They just are. Because, right, electrons, if an electron wants to get from point A to B, there needs to be it needs to be able to keep its energy or get enough energy to jump this gap. It can either jump if it needs to gain energy, or lose energy. It can jump or fall, and we'll just lose E, or it can quote unquote move if it can keep its energy and still move and still go from A to B. Metal has some interesting properties. Metal has atoms. You have your atom, and another atom, and another atom, and another atom. They form a nice crystal structure. Very cool. Metal, though, its valence energy state, the ground state for its valence electrons, is all the way out here. And now, the electrons, if I have an electron here, and it wants to get here, it doesn't have to jump anything. It can just go here, right? Or it can continue touching the lines. There is no need for it to jump, because the valence energy states for metal touch. So that's why electrons have a really easy time moving through metal, because they can just kind of keep going. Cool. Hopefully that makes sense. The electrons don't need to gain energy. They don't need to lose energy. They can just go. Silicon is more complicated. We'll do it like this. Okay, so we have this. We have our silicon atoms, and they're a little bit farther apart. And then we have our valence band. Even smaller. Okay, our valence band is here. So, silicon doesn't conduct. If the electron is here, the only way to get from here to here is to jump. And it really wouldn't, it would rather not jump. But silicon has a second energy state that it allows, and that is all the way out here. The energy state, the excited energy state for silicon, it touches. So if an electron is here, it first needs to get here. It needs to jump, but then it can just go wherever it wants, like it could in metal. And the way for this jump to happen is either through light hitting the electron, right? Your ground state electron can then go and become excited, or voltage. If your V, let's say, plus is here, and your V minus is here, you have an electron that's here. It's in ground state. It needs to get up to this state to go over to the positive terminal. It needs to jump. And we can make it jump by applying enough voltage. If you add enough volts, the electron gets to jump, become excited, and then go on its merry way towards the positive terminal. So you apply voltage to make silicon conductive. If you apply too little voltage, it will not conduct anything. And if you apply too much voltage, if you apply enough voltage, then it'll start conducting everything. But this isn't a great semiconductor in the sense of, like, if there's just enough voltage, it'll just conduct stuff. You can't do very much with a switch it's like a door that opens when someone goes through it. It's not a very useful door. I've not seen the graph of conductivity for silicon, actually. That didn't come up as part of my research. But yeah, I mean, silicon by itself is like a door that if you walk through it, it opens. Which can be good. But it's also like a bad door to stop people from going through. If you ever wanted to stop people from going through, you just couldn't. So, we add things to the semiconductors. Silicon is one of the most common ones. But there are others. Specifically for lasers, there are some that are much preferred to silicon. But for just general semiconductors, silicon's still, I believe, the most common type. So, ooh, I didn't know there was a green dot where the pen was. So your silicon You want to make your silicon... It's like a horizontal line up to a certain voltage and then it just gets linear. Oh. Oh, that's... Yeah, that is weird, huh? Nah. Wow. So. Right, so you want to make a door that you can close. It's not going to make sense until I explain how it's used to actually make a door that closes. But we add... We have our silicon block. And then we have our other silicon block. Or no, you know, we'll do it all in one. We have our silicon block, and we're going to split it down the middle. Usually these would be two separate silicon blocks that you then shove together. But for the purposes of understanding, we'll just say it's one, and we split it down the middle. And we're going to say, well, in this section, this is going to be the positive side. This side is going to be, let's say, or yeah, this is going to be positive, and this is going to be negative. Kind of predefining which way is going to be the right way, and which way is going to be the wrong way. Essentially, we want to make a system where currently this is going to be a one-way door. Before silicon is a door that just kind of opens whichever way. We don't want it to, because if it opens, you know, if it opens out of the restaurant, that would be bad. I don't know why. That analogy kind of fell flat. We want it to be a one-way door. We want the current to go this way. This way is bad. We don't want it to do that. We only want it to go one way. So, how do we do that? First, we introduce impurities, which is not a bad thing in the same sense of, like, these are impurities that we want to add because they're important. So we're going to add an impurity here. We're going to add a material. I don't know. Let me see if I can find one. Periodic table. Okay. Was it? Yeah. So we want to add a material from this row forward. For the P side, germanium, I think. I mean, it's on... No, germanium is on... Not that side. What the hell? Gallium might be an N. I think gallium nitride sounds about right. But... like, that rings a bell. I feel like I've heard of that. Anyways. So we want to add a material from this side, because they want electrons. Nitrogen in its valence shell has 1, 2, 3, 4, 5 electrons. Valence shells really want to be empty or full. Nitrogen is 3 electrons from having its valence shell full. So it really wants to just get 3 more. So we will call these holes. There could be an electron there. We want an electron there. But it doesn't need... it isn't there right now, but we want an electron to be there. The other one we will pull from the other side of the table, which is this side. And I think usually you would want something that... or not. These 3 and then these. So you would want something that has, I guess it depends on what exactly you want. Let's say we add... carbon is 4, right? Yeah, so then boron is 3. So you would add, like, aluminum or something. Aluminum, right, in its valence shell, has 1, 2, 3 electrons. And remember, valence shell wants to be empty. So we want to get rid of these. So aluminum will give us electrons, and the valence, or in the p material, or this is called our N, or our donor, because it provides electrons which are negatively charged, and this is called our P, or our acceptor, and it provides holes, which are, it provides quote unquote holes. It adds electron holes to the material, which are positively charged. So this is minus and plus. So we have a material that wants to give its electrons and a material that wants the electrons. Perfect. But how do we make them into a semiconductor? We add materials that want electrons. Oh, thank you so much for the follow, Francie Celicio? Am I saying that right? You have a nickname you would prefer I call you? So thank you for the follow. I really appreciate it. Ad break in 30 seconds. So I think we'll come back to this then. Yeah, we'll get back to this then. All right. Good time to grab a drink, grab a snack. We will be back when the ads are over. Francis? Okay. Oh, I see how that would work. Okay. Yeah, thank you for the follow. Welcome. We will get back to the semiconductor stuff once the ads are over. Sometimes they take like a good minute to start. It's annoying. Let me turn up the music, and I will just be here. Until the ads are over, when they start. There we go. Make sure to hydrate, chat. It's good for you. Welcome back from ads, everyone. Let's get back into it. So, now let me turn down the volume. Is that good? Better? Yeah, cool. We have our donor material, our acceptor material, and we have our silicon, which is going to give us the structure. Silicon makes a crystalline structure, which is good, because then we can take the silicon, and by a process, I think it's called diffusion, ? You take, essentially, if you have your, like, lattice of silicon, we're going to take one silicon and say, but, like, what if you were not silicon? What if you were the P material? And, like, here's another silicon. What if you were also the P material? It wouldn't be this much. It's usually like 1%. But we replace some of the silicon atoms in the structure with our P materials on this side. And so our P materials and our N materials on this side. Right? So we now have, I think it's called doping. Yeah, that's what it's called. Doping. D-O-P-I-N-G. Doping. So, now we have donors on one side and acceptors on the other side. The materials that are chosen as donors and acceptors are very specific, because your donor material needs to have its valence band. So we're going to note this with like different colors. Okay, because otherwise it'll be really hard to understand. We have our valence band for our donor material needs to be right below the conductor band, which is the excited state of the silicon atoms, where all of the conductor bands are connected so the electrons can travel between them freely. We need the valence band of the donor to be right below the conductor band of the silicon. And this jump is really easy to make. This jump you can make with just outside temperature energy. So, these three electrons they were here, and now they are here. They jumped up. And now they can travel through the silicon lattice. The acceptor is slightly different. The acceptor's valence band needs to be right above the silicon's valence band. And what this allows is that the acceptor can take, the silicon lattice has some electrons, but the acceptor band, the acceptor really wants those electrons. So the acceptor can yoink the silicon electrons into its own valence band. And now, the silicon is missing 3 electrons that it would really like back. So we have our valence and our conductor for the silicon. Valence, conductor. Here, let me get rid of this. Let me just get rid of all of this stuff. There is now negatively charged electrons up here in the conductor band. Conductor and valence. And positively charged holes is what they're called, because they're missing electrons. These are not positons or protons or any of that. It's just missing electrons. So there are now electrons in the conductor band and holes in the valence band. And now these two can snap together and problem solved. Okay, but now great, we have a bunch of this material, say, not like this much, and we replace this with the acceptor, an acceptor, an acceptor. Replace the other sides like this one, and this one with donors. Now these are not positively charged or negatively charged right now, but once the donors give up their electrons, they will become positively charged, because the donors had those electrons in the first place. Because what the hell? Oh, I didn't know that was the thing you could do. Okay. The donor had those electrons in the first place because it has enough protons that it needs those electrons to balance out the charge. If it gives away the electrons, now there are more protons than electrons in the donor becomes positively charged. Yes, I know it's the N side, but it becomes positively charged. And then the opposite happens on the other side. Because now these acceptors that didn't have those electrons because they didn't have enough protons to grab those electrons, right, because it only has enough electrons to even out the charge, it gave away, or it took in more electrons than it needed to balance out the charge, so now it's negatively charged. Did I do that right? Yes. Basically, this side repels the positively charged holes from moving this way, because the silicon atoms, they can still kind of share like holes and stuff because they still do have things in the conductor bands. So the silicon, the holes will move this way, and the holes will move. The holes want to move this way. Holes. These positive charges create like a barrier that pushes the holes back. Like, no, you're not allowed to do this. You have to go the other way. Or you have to stay on this side. Same thing happens on this side. The electrons want to go this way, but this negative charges push the electrons back and say, nope, you can't come here. And this stops the flow of electrons if this balance of donors and acceptors, or if this like system goes out of balance. it will stop the flow of charge. So now if I connect a battery, so now this is our material. Back. This is our material. It's still like 99% silicon, but because you only need a very small amount of these donor and acceptor things to make a semiconductor do semiconductor things. But this side has the acceptors, this side has the donors. And now right now they're at a standstill. Because the donors, which are now positively charged, I know, it's confusing. The donors are pushing the holes back this way. They are pushing the holes back. And the positive side is pushing the electrons back. The other color. The electrons back. Because it's negatively charged. Because it took in more electrons than it's allowed to have. Or than it's supposed to have. It took in more electrons. So this is now negatively charged. So, right, negative charges repel each other, like, same thing with magnets. North and north poles repel each other. Same thing. These electrons, this negatively charged acceptors repel electrons, and these positively charged donors repel holes. So now that's at a standstill. But now I connect a battery. The battery has positive on this side. And negative on this side. Right, this is our battery. Battery. The battery can steal electrons because this is positively charged. It can steal electrons from our acceptor materials. Acceptor materials. The electrons can get stolen by the battery. Which now makes them want electrons again. And the donor material will receive electrons from the battery. This side gives you electrons, this side gives electrons, this side takes them away. So, it pulls away the electrons from the acceptors, and then gives electrons back to the donors, which lets the cycle continue. This doesn't have to be a battery, but it makes it's the easiest to explain if it's a battery, because a battery isn't, the entire grid. The battery is now connected. You now have a circuit. Now this semiconductor works great. But now, what if I were to connect it the other way? If I say, okay, wait, but like, what if I want to walk through the door the wrong way? It's a push door, and I want to pull it. Or, no, it's a one-way door. The door opens inwards, but I'm trying to push it outwards. Well, then this entire process reverses. If you put the positive on this end, you put the positive on this end, negative on this end, then you have your battery in the middle. Probably could have just let that be instead of erasing it, but okay. You have your battery here. Then what happens? The positive side wants electrons. So it steals electrons. Steals electrons from the donor. And it gives electrons to the acceptor. And this then makes the acceptors more negatively charged and the donors more positively charged. And now these arrows aren't just small, they're massive. These are huge arrows with a lot of force. So they really won't let charge flow. Charge is not allowed to flow. It stops charge from moving. So that's what a semiconductor does. We can go into how it works in computers and how they use it in computers on a different day. Today's not about computers, today's about lasers. So, now, that is our ground knowledge for semiconductors. So how would a semiconductor laser work? Well, remember that the donor electrons are up in this conductive band. Please no, you do not wish to explore the transistor chapter of your life. They're interesting. Just researching semiconductors for lasers was a lot of semiconductor stuff. Maybe it might be easier to understand the rest of transistor stuff, but I don't know. I haven't gotten there yet. In college, at least. I do have to take those classes, though. Eventually. Conductive layer. This is the conductive layer. The conductive band. Now this is our valence band. And remember what happens when the electrons move between the layers? If the electron wants to go from here to here, it needs to release that energy somehow. Now how is it going to release that energy? Light. So if we hit these electrons with the exact amount of light that it takes to jump up from the valence to the conductive, right? So now we're at the same thing that we looked at with solid state lasers. If you hit it with light beam that has exactly this amount of energy, the electron will fall and give you two beams of light. The beams of light, lots of beams of light. And again, remember they're all in phase, so it's all very nice, even laser. The great part about semiconductors is that 1, they're a lot cheaper than rubies. 2, they can be electrically pumped. That is one of the biggest things with semiconductor lasers, is that I can just run a current through it and it will pump itself. Right? Because of how the cycle works. It by default puts things up here. So if I hit it with light, it'll give me 2 light, and I don't have to worry about other types of light being there and some of the other complications with optically pumped lasers. I just run current. I put voltage here. V minus here. No, oh wait. Stop it. V minus here. Right? Right, this is like battery or power or something, and it just works. It's great. if not complicated, completely like so complicated that it's very interesting how people figured out that this would work. But someone did. Someone said, "Hey, you know what would be interesting? If we just made it all complicated. But then it would be cheap." Cheap. It's all about those dollar bills. And then it's the same principle as before. You have your stimulated emission. You make more light. The light duplicates. The other good thing about semiconductor lasers is that the light you don't need to add mirrors. The inside of the semiconductor is already a very good mirror. So it will already do most of the mirroring stuff for you. And then you just let it out one end. You let your light out this end. Laser. The other thing that I should mention is how semiconductors are built is, right, like we explored it as one block where we doped one part of it with a P material and one part of it with an N material. That's dumb. No, we don't do that. That wouldn't make very much sense. So we have one block. This is our N block. We have our P block. And then we have our transition layer, or what's called the active layer, which is where the holes and the electrons recombine and all of the magic happens in this active layer. Right, P active. And then the light comes out here. It comes out of the active layer, and then you can focus it using like lenses and stuff if you want, or say, hey, that's good enough. Yeah, and that is a semiconductor laser. I think I explained everything. Let me look at this. Did I explain everything? Let's see. Yeah, that is everything to do with lasers. Hopefully that made sense. Hopefully you learned something. Hopefully this was useful to you in some way. Okay, I think that's fine. It's good enough. Now, how long do I have until I need to end stream? I mean, yeah, if you have any questions, just put them in chat and I'll see if I can answer them. There's probably something that I didn't mention that's... we'll leave that there. Do I want to do anything else on stream today? No, I think this is it. Well, let me go see if we can find someone to raid. I forgot I put everything on this side. Let's see, who do we got that's... Okay. I'm gonna do Warframe then. VTuber. Sorry, let's. Yeah, I think it's fine. I think we'll just end stream here without rating. Unless anyone in chat has a suggestion for who we should raid. Okay. Well, thank you all so much for watching. I really appreciate it. I think what I figured out is that 1 week is not that much time to research something super in depth. So I think I will probably do one of these every 2 weeks. I don't know what next one's topic will be. Probably something, to be fair, equally as complicated. That's just what's interesting to me. But yeah, it'll be in 2 weeks. I will update that in the Discord. Speaking of the Discord, if you want to join the Discord, there's live alerts, there's schedule updates. If you want to go look at the YouTube, I post my VODs there. This will be up there if you want to go look at any specific part. And yeah. Remember, take care of yourself. Dying is in fact bad for your health. I know. Surprising. Don't be like me. Get sleep. Zaman, you didn't like being reintroduced to semiconductors? That's because you hate semiconductors? No, that's fair. The semiconductor hate is valid. See, it's like a good way to describe it is like you figure out one type of laser, and then you move on to the next, and then bitch slaps you in the face. It's like, you know everything you know? What if it was more complicated? I think the only one that was better than that was the free electron laser, which is nice, I guess. It's slightly different. I didn't really go in too deep on why it exactly like self-corrects, but that sounds like quantum mechanics shit, and no, I'm not covering that. I'm not covering quantum mechanics. Alright, yeah, I appreciate it. I appreciate everyone who was lurking or watching. I hope that this was informative, this made sense. If you do have questions, like I said, Discord. If you put them in the Discord, I will answer them to the best of my ability. Also, if you put them in the Discord, I can answer them with research from later. Yeah. Discord has a stream schedule. I planning on streaming Thursday or Friday, 11 p.m. PST. Saturday, 11 p.m. PST. And then Sunday, this time, around this time. Yeah. If you like what you saw and you would want to see more, please follow. And is that it? That is it. I will see y'all next time. Bye.